All right, in this second video, we're going to talk about the different properties of heat, specifically heat flow and thermal resistance. What is heat? Well, we already defined it as a form of energy that can be transferred from one object to another. And now let's note that heat can be measured in either BTU, which is British thermal units, or joules. All right. Heat flow is the movement of the heat energy from one body to the other, and it's measured in BTUs per hour. All right, so you can notice that it's a measurement of energy over time. All right, so it's the movement of the energy. Could also be measured in joules per second. All right. And finally, temperature. These are three different concepts that I want to make sure that you understand. Temperature is the measure of those motion of those molecules within a particular material. And it's measured in degrees Celsius, degrees Kelvin, degrees Fahrenheit. Temperature is a physical, measurable property of a particular object. So heat flow, according to the laws of thermodynamics, heat always flows from a higher temperature to a lower temperature. It's much like water running downhill, is the example in your textbook. What it doesn't do, and this is where some people get confused, it doesn't flow from an area of more heat to an area of less heat. Remember that heat is a measurement of energy. All right, so if you have, for example, a larger object and it's at a lower temperature, but because it's a much larger object, the total heat energy is higher. And then maybe you have a small object, it's got a higher temperature, but because it's small, its total heat energy is going to be lower. All right, so the heat flow is going to be from the higher temperature object to the lower temperature object. So let's take a look at this example here. We have substance A and substance B. All right, A has the higher temperature. You can see that its little molecules are moving faster. They're more excited. All right, object B here has a lower temperature. Its molecules maybe are moving a little bit slower. So in this case, we're going to use the conduction method of heat transfer. So put these two objects together, they're going to touch, and heat is going to flow from the object with the higher temperature to the object with the lower temperature until they reach equilibrium. Let's talk about thermal resistance. Materials oppose the flow of heat through them. Ordinary building materials, maybe the object A and object B we just talked about, wood, concrete, metals, they all resist heat flow by conduction and convection. Radiant barriers, specifically any high reflectance, low emittance material, will also resist heat flow by radiation. So some materials are better insulators and some are better conductors of heat. The amount of thermal resistance varies by type of material. And the example in your textbook here is comparing a wood versus concrete. And the thermal resistance of wood is 12 times as great as concrete. So if you want the same amount of heat flow, you need a much larger piece of concrete. Let's give an example from our daily life. When you're in the kitchen, your cookie sheets, your pans are made out of metal because metal is an excellent conductor of heat. And you actually want to facilitate the heat transfer to maybe your cookies that you're baking. All right. But when you pull that cookie sheet out of the oven, you use a hot pad. All right. And that's made out of a material that is a poor conductor of heat. It's a better insulator because you want to increase that thermal resistance and not transfer the heat from the cookie sheet to your hands. Okay, bringing it back to the science class, thermal resistance is typically measured by R value. All right, and here is a graph of some common materials R values. So you can see that they vary. All right, we've got some insulating materials over here, cotton, fiberglass, straw, plaster, brick, concrete has a much lower R value. So the higher R value materials have more thermal resistance. They are a better insulator against heat. The lower R value materials, they have less thermal resistance and they are a better conductor of heat. We're usually interested in the higher R value materials. Now let's just throw a wrench in here, okay, and talk about R value versus U value. Right, many times, and we'll see again and again in our textbook, we'll see things measured by U value. It turns out that U value is the inverse, it's the reciprocal of your R value. So mathematically, over here, U equals 1 over R, or it's the same thing, R equals 1 over U. All right, so these two values, the R value and the U value, they're measuring the same thing slightly different ways. Your textbook is going to come back to this R value, U value study way in chapter 15. So let me take a look. We're going to jump ahead slightly. We're at figure 15.6a and comparing the thermal resistance of various materials. So you can see that some common materials, such as metals, have a low R value. All right, concrete, also a low R value. The interesting thing about concrete is that value is for 1-inch samples. Do we typically build concrete in 1-inch samples? No. And so the thicker walls of concrete can actually have significant thermal resistance. All right, moving up in the world here, we've got gypsum board. Okay, still fairly on the low R value. Wood. And now moving into the materials that we specifically use for insulation, we've got some fiberglass and rigid insulation board. And then there are some seriously high R value materials out there. As you know, price goes up. So we've got some polystyrene, some aerogel, and some vacuum panels. Interestingly, air can have an R value, and it is the value of the thin film of air that clings to whatever building material, right? And so we actually measure that, and here it is. We've got an air space with foil on one surface right here, and here's an air space with a non-reflective surface right there. All right, in this lecture, we talked about heat, what heat is, and the different ways to transfer heat. Then we moved on to some properties of heat flow, and I finished up with a description of thermal resistance and the R values of building materials. Thanks, everyone.